In the last lecture, we have studied sputtering, RRE, and plasma etching. Right. Right. This is physical sputtering, right, which is based on the momentum transfer. Okay, the momentum transfer of high energy ions. Okay, so this is a pure physical process. And the plasma etching, right, is a pure chemical process. And the RRE, right, reactive ion etching, is somewhere in between, or it's a combination of physical and chemical etching. Okay, so now let's have a brief comparison of these three etching methods, dry etching methods. Okay, first is a physical sputtering, right, including ion beam milling. Okay, and this is based on physical momentum transfer. Okay, so there is no chemical reaction, right? It's a pure physical process. And the sputtering, right, could be directional. Okay, the etch could be directional. Okay, that's because we can control the incident angle of ions, right? For example, vertically. And the poor selectivity, okay, sputtering has a poor selectivity, right? That's because the masking layer and the substrate, okay, typically have a similar sputtering yield. Okay, so poor selectivity. And the radiation damage possible. Okay, so in sputtering, it's possible to have radiation damage. Okay, right. What does radiation damage mean? Okay. Because that's because well, but it simply means that plasma, okay, actually emits electromagnetic radiation. Right? For example, okay, X-ray. Okay, so if the energy of the radiation is too large, the device inside the plasma may be damaged. Okay, so this is a radiation damage. Okay, and the plasma etching, okay, at the other end of the spectrum, okay, plasma etching is a pure chemical process. Okay, and its etch rate is much faster. Okay, the etching is much faster. Okay, and the plasma etching is isotropic. Okay, and it's more selective, right? More selective than physical sputtering. Okay, and less prone to radiation damage. Okay, right? Because the excitation energy is lower, right? From bottom top, the excitation energy becomes higher. Okay, so low exciting energy, right? Less radiation damage. Right. In between is a RIE, reactive ion etching. Okay, it's a physical and a chemical process, right? Combination of a physical and a chemical processes. Okay, and the etching is directional. Okay, the directional etching is enabled by ions. Okay, and the IE is more selective than sputtering. Okay, so that's IE. Okay, and here let me also summarize the roles of ions and the neutral radicals. Okay, in the plasma, there are ions and also neutral radicals. So let me summarize their roles in these three dry etching methods, okay, briefly. Okay. First in physical sputtering, okay, the etching is done by ions or neutral radicals. right, by ions, right? Sputtering is done by ions, or positively charged ions, okay? And neutral radical, okay, do not participate in the etching, okay, in the sputter etching, okay? Etching is done by ions. And in plasma etching, right, it's the opposite. The etching is done by neutral radicals, okay? And actually, neutral radicals arrive at the surface by diffusion, okay? So the arriving angles are random, okay? So that's the reason plasma etching is isotropic, okay? And the ions, okay, do not participate in plasma etching, okay? So etching is done, plasma etching is done by neutral radicals, okay? And the RIE, okay, the etching is mainly done by neutral radicals. And the ions play an assistive role, okay? By what kind of assistive role and do ion play? Right. First, the ion bombardment makes the surface more reactive, okay? First role. Second, ions can clear the passivation layer formed on the surface, okay? So these are the roles played by ions, okay? But etching is mainly done by neutral radicals, okay? So reactive ion etching is more appropriately called ion-assisted etching, okay? Ions play an assistive role, okay? Questions? But you also know that from top to bottom, the pressure is becoming higher, okay? So physical sputtering has a low pressure, okay? Lower pressure. Plasma etching has a higher pressure, okay? And the excitation energy is become higher from bottom to top, okay? Next, okay, let me introduce deep RIE, right? Deep reactive ion etching, right? This is the method, right, to achieve high aspect ratio structures in silicon. Okay. So first, what is a aspect ratio? Right? The definition of aspect ratio. Actually, very simple. The aspect ratio is simply the ratio of L over W, right? The vertical dimension over lateral dimension. Okay, that's a definition of aspect ratio. Okay, this is a height. Okay, you can call this H, and its width is W. Okay, or H over W. Okay, that's the aspect ratio. Okay, and deeper IE is used to make high aspect ratio structures, right? Such as a deep trench. Okay, a deep trench. Okay, but the basic idea of silicon deep reactive ion etching is an alternating etch and a surface passivation step. This process has been developed and patented by Robert Barge, okay, a German company, right? Actually, Barge is also a auto supplier, right? So you should know Barge very well, okay? Right. This process is called Barge process, okay? And every deep IE loop or Barge loop, right, consists of 3 steps. The first step is to etch silicon by SF6 plasma. Okay, so this is the RIE or plasma etching. Okay, I use the SF6 plasma to etch silicon. Okay, and the etching species is a fluorine. Okay, fluorine atom. Okay, and the second step, deposit Teflon-like polymer using C4F8 plasma. Okay, again, it's based on plasma. Okay, but now it's deposition. Okay, the first step is etching. Second step, deposition. And the step 3, remove the bottom polymer by argon. Okay, so the bottom passivation layer is removed. Okay, then this loop is repeated. Etch silicon using SF6, deposit teflon-like polymer using C4F8, remove, okay, using argon, then SF6 again, deposition, remove the bottom layer, etching, okay. So this loop is continued. Okay, so this is the etching process of deeper RE. Okay, how our deep change is etched using Barge process. Okay, right. So this is a repeat of etching, deposition, and the removing of the bottom polymer layer. Okay. So this is the deeper RE, okay, process. Questions. Okay, first question. Why doesn't C4F8 etch silicon in step 2? Why in C4F8 plasma, why there are fluorine atoms? Okay, and the fluorine will etch by silicon, right? Just like what happens in step 1, right? Step 1, we use the SF6 plasma, okay, and fluorine etches silicon. So why doesn't C4F8 etch silicon? What's your explanation? The explanation is, okay, let's see how. Okay. The explanation is right here. Okay. The fluorine to carbon ratio model. Okay. What's the fluorine to carbon ratio of C4F8? C4F8. Its fluorine carbon ratio is 2, right? So what will happen with fluorine to carbon ratio of 2? Polymerization. Yes, very good. Okay, namely deposition. It's a deposition instead of etching. Okay, right. That's the reason. Okay, that's the reason in step 2. Okay, a Teflon-like polymer is formed. Okay, so it's a polymerization instead of etching. Okay. Another question. What's the etch mechanism in step 3? Right, we remove the bottom polymer layer using argon, right? Argon plasma actually. What's the etch mechanism? Is it plasma etching, reactive ion etching, or sputtering? Right, it must be sputtering, right? It must be sputtering. Okay, because argon is a noble gas, right? So the etch mechanism is sputtering in step 3. But compared to wet bulk micromachining methods, such as the QH or TMH, okay, deep RE is anisotropic. Okay, it's anisotropic, right? It etches vertically, and independent. Okay, very importantly, it's independent of the crystal orientation. Therefore, it allows a high degree of design freedom. Okay, you can recall that, right? For wet bulk micromachining, such as the QH, right? The side walls must be 1-1-1 plane, right? So it is not possible to etch deep trenches with a vertical side wall on 100 wafer, okay, if you use a QH, okay. However, we can fabricate such trenches using deep RE on 100 wafer, okay. So now this plane, okay, this vertical side walls do not need to be 1-1-1 plane. Okay, they can be any arbitrary plane. Okay, so this is a design freedom offered by Deep RE. Okay. Yeah, but the drawback is that Deep RE is much more expensive. Okay, the Deep RE machine costs approximately $500,000. Okay, very expensive. Okay, Deep RE has an excellent selectivity to mask material. Right? For example, PR, right? Photoresist. The selectivity is 50 to 100 to 1. Okay, so which means if you etch 50 to 100 micron silicon, the photoresist is etched by 1 micron. Okay. Deep RE has a high etch rate, right? 1 to 10 micron per minute. Okay, and high aspect ratio. Okay, it's used to fabricate high aspect ratio structures, right? Such as deep trenches, okay, with an aspect ratio greater than 20 to 1. Okay, right. So this is a SEM image, right? The cross-sectional view of deep trenches fabricated using Deep RE, okay, on silicon wafer. Okay, and the next SEM image shows a mechanical spring, okay, a mechanical spring fabricated using silicon, okay, and by Deep RE etching, okay. And this SEM image shows the scalloping side walls, okay, and this is a natural result of Barge process, right? Of the natural result of Deep RE loop, okay, right? So we can clearly see the marks, okay, created by every loop, okay. So the surface etched by Deep RE is not that smooth. Okay. Deep RE consideration, right? Some issues we need to consider for Deep RE etching. But the first issue is that the etching rate is dependent on aspect ratio, or the function of aspect ratio. Okay. As we can observe in this figure, this figure plots the etch rate as a function of aspect ratio. The horizontal axis is the aspect ratio, okay, from 0 to 10, 20, 30. Okay. From this figure, we can observe that the etch rate decreases as the aspect ratio increases. Okay. And this because of this dependence. Okay, the dependence on aspect ratio. Okay, wider trenches on silicon wafer are etched faster. Okay, you see this a wider trench is etched faster. Okay, this phenomenon is actually called RE lag. Okay, And the explanation of this phenomenon is that the etching process is a mass transport limited process. Namely, the etching need to diffuse from the opening to the bottom of the trench, right? For example, we have fluorine atoms, okay? Fluorine atoms, which are generated in the bulk of plasma, okay, outside of the trench, okay? They need to diffuse from the opening of the trench to the bottom of the trench, right, to continue the etching, okay? Right. This diffusion process is determined by the aspect ratio, okay? Namely, the higher the aspect ratio, the more difficult the diffusion, okay? It will take a longer time for fluorine to diffuse from the opening to the etching front, namely the bottom of the trench. Okay, so that's the explanation. Mass transport limited process. A simple question. Okay, let's consider two via holes, okay, or two trenches. There's a masking layer, masking layer, masking layer. One is a 2 micron wide, okay, and 2 micron deep. Okay, this is 2 micron deep. The other is a 5 micron wide and 5 micron. Sorry, 5 micron deep. Okay, so it should be 5 micron deep. Okay. Which one has the higher etching rate? Which one? What's your answer?
Both will have same aspect ratio, so both will have same etching rate.
Very good. Yes, same. Okay, about same. Okay, so these two vias or trenches will have similar etch rate, right? Because they have the same aspect ratio. Okay, as we can observe in this figure, right? The etch rate is a function of aspect ratio. Okay, the higher the aspect ratio, the smaller the etch rate. Okay, so that's the issue of RIE lag. Okay, the dependence of etching rate on aspect ratio. Okay, another issue is the notching edge on SOI wafer. Okay. What is the SOI wafer? You still recall SOI wafer? I introduced SOI wafer in bulk micromachining, right? It stands for silicon on insulator, right? Silicon on insulator. Okay. So we have a device layer. And insulator, typical silicon dioxide. Okay, so this is the top device layer, and a bottom handle layer. Okay. So silicon on insulator. Okay. When we etch the top device layer, sometimes we may observe this notching phenomenon. Okay, notching edge. Okay, and please know that this bottom layer is this layer now is a silicon dioxide. Okay, the insulator. Okay, right, this is partly caused by charging of the buried oxide layer. Okay, so this buried oxide layer is charged, positive charge. Okay, right, because the insulator, so charge will accumulate on this oxide layer. Okay, and this pushes the ions into the corner. Right, remember, argon ions need to strike the bottom surface to remove the passivation layer. Okay, but because of this charging, now this incoming ions can be pushed to the corner. Okay, and the removing sidewall protection in that area. Okay, so this allows the etching to etch the corner. Okay, and causing this notching phenomenon. Okay. Okay, now let's compare dry and wet etching techniques. Okay, so this column is a dry etching, and this column is a wet etching. Okay, first directionality, or whether the etching is a anisotropic or isotropic. Okay, dry etching can be highly directional with the most material. Wet etching only directional with single crystal material. So we cannot achieve anisotropic etching on polycrystal or amorphous materials. Okay, it's only possible with single crystal material. Okay, so that's the limit of wet etching. Production line automation, good. Poor. Environmental impact, dry etching is low, wet etching is high. Right? That's because wet etching typically needs to dispose large amount of solution. Okay, so its environmental impact is high. Masking film adherence, dry etching, not as critical, right? Not that critical. Okay. But wet etching, very critical, right? Because if the adhesion between the masking film and the substrate is not good, then that masking layer can be peeled off by the wet etching. Okay, then the etching, etching fails. Right. Cost chemicals, dry etching low, wet etching high. Selectivity, dry etching, okay, not as good as wet etching. Okay, wet etching can have a very good selectivity. Okay. Materials that can be etched, right? Only certain materials can be etched. Okay, because the product, right, typically needs to be volatile. Okay, wet etching, almost all materials can be etched using wet method. Radiation damage, right, can be severe. Right? The radiation damage is mainly caused by plasma. Okay, so dry etching could have radiation damage potentially. Wet etching, none, right? No plasma, right? So obviously no radiation damage. Right? Process scale up, dry etching difficult, wet etching easy. Okay, but this basically means we can actually etch multiple wafers simultaneously. Okay, right. So that's pretty easy for wet etching. Okay, difficult for dry etching. Critical dimension control. Okay, that's important. Okay, that's the important aspect. Dry etching could be very good. Okay, less than 0.1 micrometer. Okay, or 10 nanometer, even smaller. Okay, wet etching, poor. Okay, right, because in most cases, wet etching is isotropic, so there will be lateral undercut, right? So the critical dimension control is poor. Okay. Equipment cost, expensive. Okay, for example, DBRE, right, $500,000. Okay. Wet etching, inexpensive. Right. In many cases, we can simply use a tank or a beaker to do the wet etching. Okay, so very cheap. Okay. Sub-micron feature. That's kind of equivalent to critical dimension control. Okay, dry etching, sub-micron feature are applicable. Okay, or even nanometer feature. Okay, wet etching not applicable, right, because of the undercut. Okay, so this is a reason currently in IC industry, right, integrated circuit industry, right, for example, CPU fabrication. Okay, dry etching is dominant. Okay, right, because dry etching can achieve some micron or even nanometer dimension. Okay, but in research labs, we still use a lot of wet etching, right, because of its cost and the convenience. Okay, typical etch rate. Okay, slow to fast. Wet etching, right, could be very fast. Okay, theory, dry etching is very complicated, not well understood. Wet etching is better understood. Operating parameters, dry etching, right? There are many operating parameters. Okay, for example, gas, okay, which is plasma, the gas pressure, flow rate, okay, bias potential. Okay, there are many parameters. Okay, wet etching, but there are few operating parameters. Control of etch rate, right? Good in case of slow etching. Okay, wet etching generally is more difficult. So this is a comparison of dry and wet etching techniques. Okay, next, let me introduce another kind of dry etching, namely non-plasma based dry etching. Okay, sputtering, RE, plasma etching are all based on plasma. Okay, so they belong to the category of plasma based dry etching. Okay, and this is a non-plasma based dry etching. Okay, xenon difluoride and bromine trifluoride gas-based silicon etching. Okay, I please note that this is a spontaneous etching. Right, it does not need plasma. Okay, or no external energy is required. Okay, spontaneous etching. Okay, and the etching occurs at the room temperature. Okay, right, we do not need to increase temperature. Okay, no surface tension force. Okay, because of dry etching. Okay, no charging effect. Okay, right, no plasma. Okay, so no charging effect, and it's isotropic. Okay, xenon difluoride and bromine trifluoride etching is isotropic, and it's highly selective. The selectivity of silicon to silicon dioxide, right, is as high as 3,000 to 1. Okay, so if you etch 3,000 micron silicon dioxide is only etched by 1 micron. Okay, by silicon to silicon nitride, 400 to 1, silicon to PR, okay, 1,000 to 1. Okay, so high selectivity. Another advantage is that the system is very simple. Okay, very simple etching system or etching setup. Okay, as we can observe in this figure, right? The etching setup is very simple, and we need a tank of Zener diferrite or bromine trifluoride as the source. Okay, and a vapor reservoir. Okay, and a reaction chamber. Okay, of course we need a pump, a mechanical pump, right, to create a vacuum inside. Okay, so generally it's a very simple setup. Okay. Okay, now let's take a look at a bromine trifluoride micromachining example. Okay, right, this SEM image shows the etching result of a circular silicon dioxide opening on silicon wafer. Okay, and the silicon substrate is etched by bromine trifluoride through this opening. Okay, now we can observe that the etch surface is very rough. Okay, the surface etched by bromine trifluoride is very rough. Okay, very rough finishing surface. But in addition, we can observe this big lateral undercut. Okay, right. This is a cross-sectional view. Okay, bromine trifluoride etching is isotropic. Okay, so it creates very large lateral undercut. Okay, and then we can clearly observe in this SEM image. Okay, and this figure plots the etching depth as a function of number of cycles with different opening diameters. Okay. A brief comparison of Zener diferrite and bromine trifluoride. While Zener diferrite itself is solid. Okay, it was first synthesized in 1962. Okay, and this is a chemical reaction. Okay, Zener diferrite reacts with the silicon. Okay, and the products are Zener and silicon tetrafluoride. Okay, silicon tetrafluoride is volatile. Okay, so it's gas. Okay, and the cost is $150 to etch 1 gram of silicon. Okay, bromine trifluoride is liquid. Okay, and this is a chemical reaction. Okay, it reacts with silicon. Okay, and the products are bromine and silicon tetrafluoride. Okay, and for bromine trifluoride, okay, it costs about $16 to etch 1 gram of silicon. So it looks like bromine trifluoride is cheaper. Okay, it's much cheaper than Zener diferrite. However, okay, now Zener diferrite is dominant. Okay, everybody uses Zener diferrite. Okay, bromine trifluoride is rarely used. Okay, that's because the product, okay, bromine is toxic. Okay, toxic and can damage the pumping oil. Okay, so it's a pretty nasty gas. Okay, a nasty product. And the Zener diferrite, the product is Zener, which is a noble gas. Okay, so it won't cause any harm. Okay, so that's the reason now Zener diferrite is dominant. Right, so far we have studied a number of different silicon etchings, including HNA, QH, EDP, TMH, right, Zener diferrite, SF6 plasma. Okay, it could be either RE or plasma etching, and the deep RE. Okay, so now let's have a comparison of these silicon etchings, the silicon etching techniques. First, etch type: wet, 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 dry, dry, dry. Anisotropic etching: HNA is no, right? HNA is isotropic. QH, yes, yes. EDP, yes. TMH, yes. Xenon diphoride, no. SF6 based plasma, it depends. Okay, RE is anisotropic, but the plasma etching is not. Okay, plasma etching is isotropic. Deep RE, yes. Availability: HNA common, common, moderate, moderate. Xenon diphoride is actually also moderate now, or sometimes common. Okay, note that this is a table from a paper published in 1998, right, long time ago. Okay, SF6 plasma common. Deep RE, right, still kind of limited, right, because it's expensive. Silicon roughness. Okay, HNA low means fairly smooth. QH low, EDP low. TMAH variable. Okay, remember, okay, if the concentration of TMAH is low, then the etching surface can become very rough. Okay. On the other hand, if we use a high concentration of TMAH, then we can obtain smooth surface. But xenon diphoride, high silicon roughness, right? So the surface is very rough. SF6 variable. Deep RE low. I would rather say moderate, right? Because we know that the sidewalls etched by deep RE are not that smooth. Okay. Nitrate etch, right? Low, 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 like 1 to 10 nanometer per minute. Xenon diphoride also very low. Okay, low, low. Okay, so nitride, silicon nitride, is an excellent etching mask for all these silicon etchings. Okay. Oxide etch, okay, in HNA, 10 to 30 nanometer per minute, right? Pretty high etch rate. Okay. QH 1 to 10 nanometer per minute. Okay. EDP 1 to 80. Okay. Let me enlarge it. Okay. 1 to 80. TMH 1 nanometer per minute. Okay. Very low etch rate. Xenon diphoride low, low, low. Okay. So that's the oxide etch rate. Okay. Aluminum selectivity. Right. Whether the etching attacks aluminum. Okay. No. Okay. So which means the HNA will attack aluminum. Okay. No aluminum selectivity. Okay. QH no. QH will etch aluminum as well. EDP no. TMH yes. Okay. Again, recall that we can control the pH value of TMH to make it aluminum selective. Okay. Right. Xenon diphoride yes. SF6 plasma yes. DPE yes. Okay. So actually, aluminum can serve as a mask for dry etching. Okay. Gold selectivity, quite likely. Okay. Actually, gold is not etched by HNA. Okay. But typically, we must use an adhesion layer such as titanium or chrome. Okay. Then gold may peel off in HNA. Okay. QH yes. Right. EDP yes. TMH yes. Xenon diphoride yes. 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 Okay. So gold, in some sense, can also be used as a etching mask. P++ etch stop, this simply means boron etch stop. Okay, HNA no. Yes, yes, yes. So boron etch stop is only effective for the 3 wet anisotropic silicon etchings. Okay, QH, EDP, and TMH. No, no, no. Okay, for dry etching, right? No boron etch stop. Electrochemical etch stop, HNA, it should be no. Okay, QH, yes, yes, yes. Right, similar to boron etch stop. Okay, wet etching, no, no, no. Okay, same as compatibility. HNA, no. QH, no. Okay, because of potassium ion. Okay, EDP, yes. TMH, yes. And dry etching, same as compatible. Yes, yes, yes. Okay. Cast, low, low, moderate, 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 high, high. Okay. The DPI is highest. Okay. Disposal, low, easy, difficult. Okay. EDP is difficult, right? Because EDP is a carcinogenic. Okay. So it has to be disposed in a special way. Okay. TMH, no, moderate. Okay. Dry etching, not applicable. Okay, we do not dispose wet chemicals. Safety, moderate, moderate. Low, low means it's not safe. Okay, TMH, very safe. Okay, xenodiaphrite, moderate, right? Because that's mainly because the fluorine may react with water to generate HF. Okay, and HF is very toxic. Okay, SF6 plasma, high. DPI high, okay, they are very safe. Okay, questions? No. Okay, let's start a new chapter, right? Since we still have probably 20 or 30 minutes, okay? So let's start a new chapter. And I posted the chapter on Canvas, okay? Right, chapter 6. Chapter 6, right, surface micromachining. We studied bulk micromachining in chapter 4 and chapter 5. Okay, so now let's study surface micromachining. First definition: in silicon surface micromachining, microstructures are fabricated on the surface of the silicon substrate by consecutive deposition and patterning of thin film structural and sacrificial layers. The silicon substrate only serves as a mechanical support and usually does not participate in the processing. Okay. In comparison, bulk micromachining involves the etching of the silicon substrate. Okay. But in surface micromachining, okay, the silicon substrate mainly serves as a mechanical support. Okay, and the processing occur on the surface of the silicon wafer. Okay. To better illustrate this point, let's take a look at this surface micromachining process to fabricate a cantilever beam. Okay. So step 1, okay, we deposit and pattern an oxide thin film layer. Okay, this oxide layer is coated and patterned. Okay, and this layer is called sacrificial layer. We'll explain in very soon. Okay, why this layer is called sacrificial layer. Step 2, deposit and pattern a polysilicon layer. Why this layer is a structural layer. Step 3, release the polysilicon cantilever by etching away the oxide layer, right, formed in step 1. Okay, so we can see this oxide layer is etched away. It's a sacrificed. So that's the reason this layer is called sacrificial layer. Okay, there's a polysilicon layer is a structural layer. Okay, that's a layer to form the cantilever beam. Okay, to form the structure of the cantilever beam. Okay, and this cantilever beam is a freestanding. Okay, after the bottom oxide layer is removed. Okay, so this is a standard surface micromachining process. Okay, and we can see that the silicon substrate serves as a mechanical support and it does not participate in the etching process. Okay, no etching of the silicon substrate. Right, to give you a better idea, let's compare surface and the bulk micromachined pressure sensors. Right, this is a cross-sectional view of a bulk micromachined pressure sensor. The sensing element is this silicon diaphragm. Okay, when a pressure is applied, the silicon diaphragm deflects, and that deflection is detected by the piezo resistor. Okay, and so that's how we measure the pressure applied. And this silicon diaphragm in bulk micromachining, right, is formed by what? By bulk etching the silicon substrate from the backside. Okay, so this cavity is formed by bulk micromachining, or this diaphragm is formed by bulk micromachining, by bulk etching of the silicon substrate. Okay, and we bond this silicon die to another substrate, okay, to form a sealed chamber, a sealed cavity. Okay. Right. Thus, the left figure shows the cross section of a surface micromachined pressure sensor. Now we can see that the diaphragm, the sensing element, okay, is formed by thin film structure layer, and the cavity underneath is formed by removing the sacrificial layer by sacrificial etching. Okay, so you can see it's different from the bulk micromachined pressure sensor. Okay, so we can clearly observe the difference between surface micromachining and bulk micromachining. As I just mentioned, right, there are two types of thin film layers in surface micromachining. Okay, structural layers and the sacrificial layers. The structural layers can be polysilicon, silicon nitride, metals, polymers, and the sacrificial layer can be made of oxide, PSG. Okay, PSG stands for phosphosilicate glass, polysilicon, polymers, or metals. Okay, all kinds of metals. Okay, so we can observe that in many cases, the same material can be used as a either structural layer or sacrificial layer. Right, for example, polysilicon, metals, and the polymers. Okay, they can be either structural layer or sacrificial layer. Preparation methods of thin films. Okay, these methods mainly include thermal evaporation, sputtering. Okay, now that we have discussed sputter etching, and it's very interesting that sputtering can also be used for thin film deposition. Later we will have more detailed discussion. CVD, chemical vapor deposition, okay, and the spin coating. Okay, previously we used spin coating to coat polymer thin film or photoresist thin film. Okay, let's start with thermal evaporation. Thermal evaporation is one of the oldest thin film deposition methods. Okay, it actually has a history of over 100 years. Okay, so a fairly old thin film deposition method. It is based on the boiling off or sublimating of a heated material onto a substrate in a vacuum. So we need to heat up the material. Okay, typically we need to melt the material. The material to be deposited is heated to a temperature where the vapor pressure is large enough to obtain reasonable deposition rate. And to avoid contamination and the reaction at the source, the pressure is very low. Okay, typically less than 10 to the power of -6 torr. Okay, torr is a pressure unit. Okay, 1 torr is simply the pressure generated by 1 millimeter mercury column. Okay, that's 1 torr. So 1 atm, right? The atmosphere pressure is equal to 760 torr. Okay, and thermal evaporation is typically carried out in very high vacuum. Okay, 10 to the power -6 torr. Okay, so there are only very few gas molecules left. Okay, the purpose is to avoid the contamination and the reaction at the source. Okay, the material to be deposited. Okay, otherwise, the material will react with the gases. Okay, so we just mentioned that. Okay, thermal evaporation is carried out inside a vacuum chamber. Okay, and we typically call this a bell jar chamber. Okay, because it looks like a bell. Okay, and the vacuum inside is created by a two-stage pumping system. Okay, a mechanical pump, okay, for rough pumping, and a high vacuum pump. Okay, this high vacuum pump can be either diffusion pump. Okay, a diffusion pump is shown here, or a coil pump. And the source is placed here. Okay, source is the material to be evaporated. Okay, so it's heated. Okay, it's heated up. Okay, and the wafers. Okay, the wafer to be coated are placed above the source. Okay, so this is a setup of a thermal evaporator. Heating techniques. Okay, the techniques used to heat the material to high temperature. Okay. The most straightforward heating technique is probably resistive heating. Okay, well, we should know this very well. Okay, the heating element is simply a resistor. Okay, then we apply a large current. If we apply a large current, then joule heat is generated. Right, this heat is equal to I square R. Okay, proportional to the resistance. Okay, proportional to the square of the current. Okay, it's called joule heating. And this heating element can be either a spiral coil or a dimpled bolt. Okay, and typically you can use a tungsten to make these heating elements. And the second heating technique is RF heating. Okay, we use a RF signal to remotely heat the source. Okay, right. We use an RF coil. Okay, so yes, we can see that this bolt or this crucible is surrounded by RF coils. Okay, right? The IF coil is not in direct contact with the charge. Okay. And this IF signal, okay, when we apply IF signal to these coils, okay, eddy currents can be induced in the charge, right? The material to be evaporated, okay, and creating heat. Okay, that's the operating principle of IF heating. Another heating technique is E-beam heating. Namely, we use high energy electron beams to heat the material, to heat the charge. Okay. The operating principle can be explained using this simplified schematic. Okay. First, this filament. This filament is an electron beam source, right? It can generate electrons. Okay, and the electrons are extracted and accelerated by this accelerating grid. So we apply a positive voltage to this grid, okay, to extract and accelerate electrons. Okay. Then we apply a magnetic field to bend the electrons, to bend the electron beam, okay, to make the electron follow this circular trajectory. So what's the direction of the electrical field? What's the direction? The Lorentz force, right? Here we need to calculate Lorentz force. F is equal to Q V cross V, right? Okay. V is in this direction, okay? Velocity of electron. So what's the direction of magnetic field B? It actually should be perpendicular to the screen and pointing out, right? They should be pointing out of the screen, right? We know that electrons are negatively charged, right? Q is negative, okay? So this magnetic field should point out of the screen, okay? Then this Lorentz force will bend electrons in this direction, okay? Questions? Okay. So we use a high energy electrons to bombard the charge. Okay. Right. After bombardment, the energy of electrons is transferred to the charge or source. Okay. And in some sense, the charge is heated locally. Okay, the spot which is bombarded by electron beam. Okay, so it's in some sense it's heated locally, and the crucible can stay at a lower temperature. Okay, unlike resistive heating. Okay, for resistive heating, right, the heating element must have a temperature at least the same as the charge. Okay. But for E-beam, okay, the crucible can stay at a lower temperature. So the crucible can have a very long lifetime. Okay. Among the three heating techniques, okay, actually E-beam heating is dominant now. Okay. So most E-beam evaporator use most thermal evaporators use E-beam heating. But this figure shows the electron beam E-beam evaporator in our clean room. Okay, so we have E-beam evaporator in on the third floor of engineer building. Okay, so probably some of you already know that we have a clean room on the third floor of an engineering building. Okay, and this is an e-beam evaporator. Okay, this is a Barge chamber. Okay, so wafer placed inside this chamber. Okay, and this is a control panel. Okay, and to the right, okay, this is the power supply for e-beam source. Okay, and this model, the model name is BJD 1800. Okay, that's an e-beam evaporator. Next, let me introduce a very important concept in vacuum technology: mean-free pass. Okay, as shown in this figure, a gas molecule. Okay, let's focus on this gas molecule. When it travels in the space, it can collide with other molecules in its path. Okay, many collisions. The average travel distance of a molecule between adjacent collisions is called mean-free path. So mean-free path is simply the average distance of these segments. This one, this one, this one, this average value of these adjacent collision distance. So that's the mean-free path. And it has been derived that this mean-free path is equal to, okay, lambda is equal to 1 over square root 2 pi d square n. N is a gas concentration. So it's very obvious that when n decreases, okay, lambda increases. Okay, so if we reduce the gas pressure, okay, mean-free path will increase. Okay, because there will be less molecules. There will be less molecules in a space and less collision. Okay, so the mean-free path become longer. Okay, that's kind of common sense. Okay, or intuition. Okay, D is a molecular diameter, and at the room temperature, and for air, if we consider air molecules, okay, then lambda is equal to 0.66 divided by pressure in Pascal. Okay, the unit of lambda is centimeter. Alternatively, if we use a pressure in torr, then lambda is equal to 0.005 divided by the pressure in torr. Okay, the unit is a centimeter again. Okay. And this figure plot the mean-free path as a function of gas pressure. Okay, log of gas pressure. In the previous slide, we mentioned that thermal evaporation is typically carried out at pressure less than 10 to the power of -6 torr. So how large is the mean-free path? When the pressure is 10 to the power of -6 torr. How large is mean-free path? Then lambda is equal to 0.005 divided by 10 to the power of -6, which is how large? (5,000 centimeters), right? So it should be, well, 50 meters. Okay, so when the pressure is 10 to the power of -6 torr, right? The mean-free path is about 5,000 centimeters, which is 50 centimeters. How large is the deposition chamber? I would say probably less than half meter. Okay, less than half meter. So a mean free path of 50 meter means what? It means the atom leaving the source, okay? Let's assume source is somewhere here, okay? Leaving the source can directly deposit on the wafer without a single collision, right? Because the mean free path is 50 meters. And now the distance between the source and the wafer is less than 0.5 meters. So there will be no single collision. And we call this type of deposition line of sight deposition. Okay. Namely, right, we can treat the source as a light source. Okay. If the source cannot see the area, then there will be no deposition. Or there will be shadowing effect of this type of deposition. Okay. What's the shadowing effect? Very simple. There will be no deposition on shadowed area. Okay. But if we consider the source as a light source, okay, so it's shadowed here, then there will be no deposition. Okay, so this line of sight deposition leads to this shadowing effect. And this shadowing effect could be good or could be bad. Sometimes it's bad. Like for example, if you want to form a continuous interconnection wire, right, then it's bad, right? Because it results in a broken wire here, an open circuit, so it's bad. But for lift off, okay, I believe you still remember lift off, okay? It is good, right? Because there will be no deposition on the vertical sidewall. Okay, then it's good for lift off. Any questions?